This is going to be a talk. I used a cheap trick, which is to give an intimidating talk title. Where people are afraid. They say, "Okay, this is a talk. We're not going to something," and then even worse, abstract. So then people don't have high expectations. So in terms of what they might be able to, or might not come, but that's just also a way to. Anyway, so I will try to tell you about, explain you that, try to convince you that this is these Liouville quantum gravity and these type of things, which have been developed a lot by Jason and Scott, which are my co-authors on the story I'm going to tell you, is fun and elegant, and the results are very, I hope the one I'm going to tell you, sort of easy to see why there is some, lot of elegance in there. And so maybe I'm going to start with the goal will be mostly to state the result so that you see what it says, and that it's actually just, various elementary building blocks that come together. And the idea, the global philosophy, is that we want to show or explain why, on the one hand, the story about conformal loop ensembles, scaling limit over ON models, conjectural scaling limit over ON models, on the one hand, are really one very natural object that you want to consider when you want to mix it with this other structure, which has to do with Liouville quantum gravity and which has, taking the exponential of some constant times the Gaussian free field, and where somehow some of the magic that the physicists understood early on happens, and where also the contact can be made fairly directly with, the fairly recent developments on planar maps done by Nicolas, Grégory, and others who are looking at, Grégory Mirmont, who are looking at these planar maps with large faces, stable maps, and sort of the other, continuous metric spaces beyond the Brownian maps, the other ones which have these holes and bottlenecks and all these. So the first, our first player in the game will be an old friend, which are just as, stable subordinators, stable processes. So I just want to remind you very briefly that, when you have, so I never remember if there's one asymmetric stable processes. And, you take alpha, imagine that you take some alpha smaller than 1, and then you take, on the real axis, you take a Poisson point process. I mean, sort of this would be time, and this would be x, with intensity dt times dx over x to the alpha plus 1. So, the plane, so you would have on x positive here, you would have, points that fall here. Okay? These are going to be the jumps or subordinators. They fall here, and because this explodes when x goes to 0, you have, lots of small jumps near the axis here. That's here. And then when you have that, at time t, you can just sum the values of all the values of x that have fallen to your left. And in this way, you define this sort of stable subordinator, which is this process st, which is a process with, stable subordinator, which is the one, because you chose this power law here, is going to be the one that has a nice, scale invariance embedded property, and that's sort of an increasing process because we took x to be positive, and this works as long as alpha is smaller than 1. Now, a natural thing you can do is say, well, you can define a process that both positive and negative jumps, right? Stable subordinator, the difference between two stable subordinators, and then you have an additional parameter that I will call I here, which is somehow the ratio between the intensity of positive jumps and negative jumps. So one instance of this guy could be, I times st minus an independent copy s prime t. So that will be a subordinator, it has positive jumps, has negative jumps, but sort of the intensity of positive jumps is I times the intensity of negative jumps. So that's the asymmetric, one version of the asymmetric, stable subordinator with this I. Now, one of the nice stories in probability, I remember that was one of the first nice things I felt, oh, that's cool, that, which in some sense is just stochastic calculus baby version, is that, there's this story that when alpha is larger than 1, this doesn't work because you have too many positive jumps, the total sum of the positive jump goes to infinity. But, there's a way somehow to, because alpha is larger than 1, the expected value of the large jumps becomes finite, and therefore you can subtract by, doing Liouville compensation by subtracting, somehow the mean, whatever that means of these positive jumps. You can still make sense of, the stable subordinators will have only positive jumps even when alpha is larger than 1, and you have a similar object like that here. So these stable subordinators, which don't have necessarily positive and only positive or only negative jumps, they're classified by alpha, where 1 over alpha would be the, the scaling exponent that you have in your picture, and I, which would be sort of the ratio between the intensity of positive and negative jumps. So I just want to emphasize that when alpha is between 1 and 2, then basically the you have this Liouville compensation story, so things are a bit more tricky. There's something weird going on in terms of the total amount of small positive and small negative jumps, which sort of is infinity minus infinity, but sort of compensates. Okay, that's going to be our first player, and our first player I'm going to use also just introduce already a new. A variation of this guy. So here the idea is to say, if I'm somewhere at S, if I look at the one which has alpha smaller than 1, then it's during time dt you have an intensity of jumps that goes up. You add you go to S plus h with intensity basically dh over. The intensity 1 over h to the alpha plus 1, and then you go to S minus h with intensity 1 over h to the alpha plus 1. Or here you would have an I here if you want to have the... and now you can sort of do a little bit of like what we like to do, like H transform type stories. You can twist this process a little bit. For instance, imagine you start somewhere where you're positive, and you want it sort of to remain positive, so you just have to introduce a natural, type of martingales that you want to introduce in order to define sort of the changed measure for the twisted thing. And one very natural way to do is to do the following: is to say that if I'm at S, right, I'm going to jump up, and now I'm going to do S plus h to the power alpha plus 1, and here I'm going to do S to the power alpha plus 1. Right? And similarly here, I can do S minus h to the alpha plus 1. Oh, sorry, the other way around. I'm sorry? Not the red one. Okay, so here I take S to the alpha plus 1 over S plus h to the alpha plus 1, and here you take S to the alpha plus 1 and S minus h to the alpha plus 1. Right? So if you do this type of thing, then you see that with respect to the previous thing, then your process to the power 1, I mean to the thing to the power 1 over alpha plus 1, you will get a nice martingale. So in some sense, you see for the very small jumps, the difference between this one and the previous one is very small. Okay. It only affects the large jumps, and they're only finitely large jumps on a finite time interval. So somehow you can see that this guy will be absolutely continuous with respect to the other one on sort of small times. And why is it natural to do that? Because you can view this in terms of it'll come out later. It's a bit like a fragmentation coalescence process. You can view this this thing here would be like something like I'm sitting there. This guy has some sort of a partition function. I mean, at S, the partition function would be something like that, or 1 over this, right? If the partition function at S, the energy at S is 1 over S to the power of something, then, if I have 2, now here I have a product, so of the same thing. So then you want to say I'm going to split into 2 things that each of them have a partition function or sort of energy type thing, which is 1 over H to the power alpha plus 1 and 1 over S minus H to the power alpha plus 1. So this, you view this as a splitting of S into H, S minus H. This, you view it as, some H comes on top of you and you add it up. Now, and it costs you, and you'll see exactly where this comes from. And of course, Nicolas there says yes, because he knows all these very well, because in the context of peeling of planar maps and ON models, this is the type of thing you want to do, because you are going to. Anyway, so one important thing here is that it's very natural here to put indicator function of H smaller than S over 2, because if I split S into 2 pieces, then I can decide to order it by the larger one first and the smaller one next. So the S minus H is the larger. I decide that this is the larger one and this is the smaller one. Okay, and therefore your jumps will have that type of. You can decide that. Okay, so that's a natural sort of variation from this one. It's sort of pretty clear to understand what this guy is doing when you take alpha smaller than 1, but when alpha is larger than 1, you can define it exactly in the same way with a type of compensation, because the compensation comes out of by doing the martingale H transform from this one here.
Oh. Markov process that's absolutely continuous with respect to the stable one?
Yeah, when you start with. If you start a positive thing, it will be absolutely continuous on a finite time window. And of course, from what I told you, somehow it's quite natural to want to view this as a fragmentation thing. So the H might continue evolving according to the same splitting thing, and it's a sort of fragmentation story. And in view of the fragmentation type idea, you have this. It will come out, later that you want this I to be smaller than 1, because you want your object to, eventually should, disappear, should not explode, right? So this S should eventually, the things should become smaller and smaller and smaller and then get away, and therefore you need more negative jumps than positive jumps in this picture. You need to be pulled down, so which means that the intensity of positive ones versus negative wants to be negative. Okay, that's the first player. Now, second player is conformal loop ensemble. And of course, in these coming 5-10 minutes, I'm not going to. I'll just give a glimpse of what a CLE is. There are 2 sorts of CLEs, and of course, you sort of see where I'm going to come to. The first one are the CLEs that have to do with simple loops. So these are collection of SLE kappa type loops for kappa between 8/3 and 4. So the numerology, don't need to worry about it. It's a collection of fractal simple loops. Every point, they are random. Every given point will be almost surely surrounded by a loop. So the Lebesgue measure of what is left outside of the loop is 0. And not only the Lebesgue measure is 0, but the dimension is actually, you can compute it as a function of kappa, is strictly smaller than 2. And the idea is that this CLE kappa, if we think that SLE kappa should be the scaling limit of one single interface, with a model with appropriate chosen boundary conditions, these CLE kappas should be the collection, the scaling limit of the whole collection of loops that arise in the scaling limit, or the outermost loops that arise in the scaling limit when you're looking at a model with sort of uniformly chosen boundary condition. And this is known to be true now for kappa equal 3 for the scaling limit of the outer boundaries of the Ising model, for instance. That would be one example. Okay. kappa equal 4, the guy at the here is related to the Gaussian free field level lines by work of Jason and Scott. And okay, so that's CLE kappa. When kappa is smaller than 4. Now, one thing we did, and this is not what I'm going don't want to explain now, but it's really playing an essential role in the entire story, is that when I sample, so these are the supposed scaling limits of, you can view it at two objects. You can view it in this way. One would be the scaling limit of the ON models, the dilute ON models, when if you know about them, and that's the conjecture. And the other one would be the following. I take a Potts model with Q equal 2, 3, or 4, with plus boundary, with the boundary condition which is uniform. So the boundary would be one color. And then you take the scaling limit of the cluster of that color at the critical value. So this will be some fractal object like that with holes. Right? And the idea was just to say that this should be the scaling limit of that guy. Now, what we did in earlier work, partially in the view of this sort of large-scale project that I sort of going to try to show you a piece of, is that we defined some random curve that is just within the CLE carpet, and that you should interpret, and that we can interpret, that satisfy lots of axioms that characterize it. And these axioms are basically saying that this guy is critical percolation within the carpet. So you sample the CLE carpet, then you have a fractal object, a scale invariant object. It's very thin. There are lots of holes, so you have a lot of obstacles, very difficult to go through it. But you can still make sense, because it's a scale invariant object, just like the Sierpinski carpet. You can make sense of something that would play the role of critical percolation within the carpet. So this thing has the idea, when I hit a hole, it's always an obstacle here. I'm not going to toss coins. This is going to come back later. So hole is always your enemy. So this thing is somehow leaves the cluster on the right and the empty stuff on the left. And so when it hits a hole, it leaves the hole on the left. Right? If I hit that hole, I have to go around it this way, because the hole is it's interface between white and black. You sample white and black, of course, in a very asymmetric way inside the carpet in order to be able to make it through it. And all the holes are black, and you leave black on the left and white on the right. That's the basic idea.
And this curve stays in the zero Lebesgue measure part.
Yes, that's right. And so what we prove in these earlier papers is that this curve here is actually an SLE 16 over kappa curve, which should not surprise you if you think of the interpretation of FK model, Ising model, because you know that if I take you, or if I give you a Potts model, the usual way we like to view the Potts FK representation thing is start with FK, color the clusters, and look at the colors you get. And then you get Potts. But it goes the other way. You can start with Potts, take a cluster of Potts, do Bernoulli percolation in the cluster of Potts, and then you get FK clusters. Right? So this guy will be, this somehow is exploring inside the Potts guy. It's exploring the FK cluster that is inside the carpet, because the FK clusters will be subsets of the Potts guys. Okay. Now the main point I want to emphasize is that behind the scene here is very important that there is you can discover both Potts and FK simultaneously in some sense, meaning that the natural thing you want to do is you start your blue thing, and as soon as you hit a black loop, you attach it. You go around it. And you leave it on your left, and you continue on the right. Right? And by doing that, if you believe in these axioms that this guy is the critical percolation in the interface, if you believe in that, then it's clear that this object, the blue plus black guy, will have a conformal Markov property. That once I finished exploring the black guy, what remained to be explored is just, CLE plus critical percolation, the remaining of the CLE in front of me. And when I am in the course of discovering partially a black thing, because of the definition of CLE, I know that, first thing I need to do is complete the loop. And completing the loop is just doing a plain SLE from here to there. So what I want to just, forget about the small details, what I just said. It's just that it's very natural, to do this thing, to explore. You launch the blue thing, and each time you hit a black loop, you trace it, because in some sense you're discovering in a Markovian way, a bit like in the SLE type usual way, the space in front of you, and what remains to be explored, the law of what remains to be explored has a nice structure that you can understand, and so you are really doing IID iterations of IID type structures.
So
yes?
In your picture, it looks like you'll hit the same, originally, you'll hit the same loop.
Exactly.
More than once.
Yes.
So if you attach it.
So I attach it, but then the blue thing is going to bounce to the same loop. So somehow the blue thing is going to hit the boundary. That's another way to.
Hit the same loop that you just attached. You don't do any attachment again. You just.
No, it's there, so it plays the role of boundary. So it plays exactly the same role as this outer boundary here at the beginning. It's part of the boundary, right? Okay, so that's CLE kappa. You can do the same type of thing for kappa prime. So the CLE kappa prime would be, and I don't want to spend too much time because then I'll be out of time, but one important piece is that you have CLE kappa prime for kappa prime larger than 4, which would be the scaling unit of the FK model. Okay, and then you can do something similar, which says, but the something similar you want to do is slightly different, because then the idea is that you're going to do this scaling limit version of what is called the fuzzy Potts model that Jeff knows very well, which is just you start with FK model, you color the FK model, you decide to color them, the clusters according to 2 colors using some coin, not necessarily 1 over Q, 1 minus 1 over Q coin, and then define clusters of loops of the same color, and then you look at the interface, and then it has a similar type structure. But I don't want to. I just want to emphasize that there's a counterpart for the non-simple loops as well here. So that's our second player. Now, third player I want to have in the game is Liouville quantum gravity, and my crash course on Liouville quantum gravity will go as follows. So you have the Gaussian free field in 2 dimensions in the domain D. So usually the way the Gaussian free field is defined is you take 0 boundary conditions in your domain D, and then it's defined as a Gaussian process with certain covariance structure given by the Green's function in that domain. If you know what the Gaussian free field is, fine. If you don't know, you should just think, the Brownian motion is a natural oscillation of, a natural random curve, so the natural infinitesimal random oscillation of a violin string, right? View it like that. And the Gaussian free field is just a natural infinitesimal oscillation of a tambourine skin, attached on the boundary, 0 boundary of your domain D, and then it will going to fluctuate like a bit like that. And that would be the natural, it's the counterpart of 1-dimensional Brownian motion where you replace time by 2 dimensions. Now, the nice, what makes it so fun to play with the Gaussian free field in 2 dimensions is that as opposed to the Brownian motion, it's not a continuous function anymore, right? It's like plus infinity, minus infinity, everywhere. So because somehow, the tambourines, okay, I'm not going to give a course on Gaussian free field, but that's sort of and it's not a function. It's only a generalized function, so it's something very rough. It's very difficult to describe. You have to be very careful when you take things like taking the exponential of this guy or things like that. On the other hand, it satisfies, because it is defined, it is a natural counterpart of Brownian motion, it satisfies some equivalent version of the strong Markov property of Brownian motion. Okay, and therefore, meaning that if I discover the fluctuation of my tambourine skin all the way here to here, what's the conditional distribution of what is there? Well, it's just a natural fluctuation of the tamarind skin in my new, in the new domain here. So you read the boundary values that you have read here, and then you attach it like the same way here, and the law what remains to be discovered will be a Gaussian free field in the remain to be discovered domain. And this Markov property is the reason why this object is super relevant as soon as you look to physical type things where you try to understand things like field theory or interactions, because you want the interaction to go from place A to place B in space and not jump in a telepathic way. And sort of that's the type of Markov properties you want somehow in your picture. Okay, so that's a two-dimensional Gaussian free field. Now, for reasons that have to do with what they call quantum gravity, is that you want to understand what is the natural oscillation away from the Euclidean distance in two-dimensional space. That's one way to view it. Okay, what's the natural way you can move away from Euclidean distance? And you think a bit, and you say, well, a good object to investigate would be something like exponential of gamma times gamma, where gamma is a constant. Okay, so I'm not going to go in details, but that's sort of a fairly natural thing to do because you want the Markov property to hold. You want some sort of notion of scale invariance, in your picture. And therefore, you want to start on, it's a natural thing to do to try to say, well, let's use this as an area measure, say, for instance, for your and try to, understand the fluctuations away from Euclidean, area measure in a natural sort of Markovian way. And if you do that, well, what happens is that it is possible, even though gamma is not continuous function, you use a very, natural little approximation, the approximation scheme you prefer. So you can, for instance, make sense of replace the value at a point by the mean value on a small circle around you, which this is finite object, which is well defined because it's, and then you let the radius of the circle go to 0. This thing is going to explode, but if you compensate it and renormalize it in the right way, it will converge to something. So this has been explained at a number of places. I guess maybe the first ones to do that were Duplantier and Sheffield in their first Liouville quantum gravity papers. But so this is something one can do. So the idea is you have a gamma positive gamma, and then you define this. And of course, the larger gamma is, the wilder sort of the fluctuations of these area measure are going to be. And the important thing is the Gaussian free field is invariant under conformal transformations. Okay, so if I have a Gaussian free field in a domain D in 2 dimensions, and I map it conformally onto some other domain, the image of the gamma will be just a Gaussian free field in the other domain. So that's one important feature. And therefore, you can look at what happens to this area measure, when you transport it, when you use conformal invariance. And what happens is that because of the renormalization scheme, so of course you have a gamma, you took the exponential, so you have to be a bit careful, with what happens. Plus, you have to be careful with the fact that there is a renormalization scheme that went on that you had to, and in order to define the renormalization scheme, you had to use the actual Euclidean measure that you have around you. You have to normalize by, area of, by local radii of circles. So what happens is if I, look at the measure defined by this here, then I take the image of this measure on the conformal map phi, then what you get there is basically the exponential of gamma times a Gaussian free field here. So it will fluctuate somehow in a similar way, but there will be a bias, and the bias will have to, gamma plus, and here the bias will come like 2 over gamma plus gamma over 2 times log of phi prime at z. So basically, depending on how much you did blow up things in the neighborhood of z, you will change the compensation scheme, and so this 2 gamma and gamma, they disappear. So this one just has to do with the fact that you're looking at the area measure, and then the other one that you have there, the one with the gamma squared just comes from the renormalization scheme, the epsilon squared story on balls that you have there. So the natural thing to do in that context is to define. So what do you want to define to be the random, they call quantum gravity surface. The natural quantum gravity surface is, if I give you a domain D and one of these area measures has behind the scheme a Gaussian free field behind them. Okay? And then you want to say that this is going to be defined because you want to use conformal invariance. It's going to be defined modulo, as equivalence classes, meaning saying that this is the same as that. Okay? So you just say, well, it's not the structure given is D, and this gamma, if you want, and this transforms in when I transfer, in a covariant way, in that way. So we have to be a bit careful because if you define it this way, then this should be invariant on the Möbius group of Möbius transformation, and you end up with a bit of trouble because I just said that if you apply the group of Möbius transformation here, you change it. So how do you go about it? Well, what happens is that you can add marked points to your domain. That's one way to do it. And then if you add 3 marked points, there's no group of Möbius, you don't have to worry about the fact that your object has to be invariant. Or you can define harmonic functions, special harmonic functions in your domain. And so to cut the story short, one important structure that you get is the following, is what they call quantum disks. And a quantum disk basically is this structure here. Okay, this, it's the object that has no mark point. Right? You want to find, the way to define a structure which somehow has no mark point, or meaning that the mark point is given intrinsically by the object itself. And so quantum disks is, you'll see it in a moment. In some sense, what I'm going to describe to you a bit later is the equivalent definition of what a quantum disk is. But now this object is going to use the Gaussian free field here with free boundary conditions in the domain D. The Gaussian free field with free boundary conditions in domain D is defined up to additive constants. Being defined up to additive constants means that this thing is defined up to multiplicative constant. And so that will mean that the natural definition of what one wants to call a quantum disk will be given by an infinite measure. It's a scale invariant measure. Okay? Because, it's if I multiply, you want this, when you multiply by a constant, it should be the same measure somehow. When you multiply the metric by a given constant, which corresponds to shrinking the domain or making it larger, it would be the same object. Okay.
And the probability measure is replaced by a
Yeah, there exists an infinite measure, right, on equivalence classes of objects like that. That is completely conformal invariant. That's basically the story. And this equivalence class this is what one wants to call a quantum disk. And you can decompose it as something which has to do with the length of the boundary of that disk, which is chosen according to dx over x to the alpha plus 1 times some measure of a unit quantum disk. So you should really view it as there's a random object which has a finite, in a finite piece, and then you take the scale invariant version of that, and that's an infinite measure. Okay. So now how does the theorem go? I want to state, because time is running. So the theorem I want to state goes as follows. So there are a number of other versions. This is sort of the easiest one. You take this picture here. You take a CLE kappa and take a CLE kappa with the exploration mechanism. Discovered. So the CLE kappa plus the percolation in this object there. So I want to just emphasize one thing in this exploration picture, as Russ said. There are two. If you take a point here, you start the exploration at -1, and you always target 1, say. When you do that, the domain that remains to be explored, there are two ways in which this domain can make jumps. The first one is when you find a loop, you add the loop. Okay. What happens to the length, of the domains that remains to be explored, when you add a loop, the length becomes larger. Okay? Because the domain that remains to be explored, seen from here, the length was that, and now I add a loop, I just add the length of the loop. Now, on the other hand, it happens that this trunk, this percolation thing, might hit the boundary of the domain. So, you might be exploring all this stuff, and then this FK guy hits the boundary here. So what you do in that moment is that you cut off all this. You split it into two pieces. Right? Here you split, and the sum of the length of the two pieces is going to be just the length of the thing you had before you. Okay? So of course you see where I'm trying to go for. So now I have this exploration mechanism here, and then take an independent disk, quantum disk. So here, when I say take an independent quantum disk, I take a disk of size 1. Right? You fix a size, and you just go in and explore this guy. That's a probability measure. Size meaning the length, the sort of the length of the boundary, which is some object that you can define in that context. They're independent. Now, you look at the process. So, you have a movie, you are exploring, and along the way, you are either exploring, all the loops are on the one side here, or you are exploring, sometimes you discover a bubble, and inside the bubble there is, it's a quantum something, right? It has the exponential Gaussian free field sitting in there, right? So they come in a natural way here. You want to say, yeah, of course it's going to be Poisson or something. No, not of course it's going to be Poisson at all, because there's a very big correlation on what happens to the surface here and there, because it's the same Gaussian free field you use, right? So you can't just say that what is here, surface here is independent from the surface there. Right? I mean, here, the length is the same seen from this side, seen from that side. So, I mean, and there are some other things that happen that occasionally, you cut out pieces here. So, and then you cut away something which, again, is a quantum, a quantum surface. Okay? So the theorem is that the quantum surface point process, of ordered of these ordered, quantum surface that one discovers, and cuts out. So it's, on the one hand, the bubbles that you discover in the order of discovery, and on the other hand, the thing that, when you go to that point here is you're just going to cut out, is a Poisson point process of quantum disks. So given time, I need to be, So how does this Poisson point process of quantum disk work? Yeah, it's from that measure. Each of them is given by that measure. But you have to explain, what the size of the things are and what the relative ratio of the, the going to the inside, going to the outside is going to be. Okay? So here I'm cheating slightly when I say it's a Poisson point process of quantum disk. The idea is going to be, it's that process. Right? So, meaning that what you're going to have is that I'm sitting here, and the jumps that you're going to make here, each disk has a certain boundary length. The jumps that this process is going to make, so each of the negative jumps of this process here will correspond to cutting out a disk of size h. So basically here, this corresponds to those guys. Each time the ones that correspond to discovering a loop, right, they will correspond to the positive jumps here. And the process S you have here is nothing else than the evolution of the boundary length of your process. So now you're going to tell me, yes, but you said H is smaller than S over 2, so how do you make sure that, well, the idea is each time I split the thing into two pieces, I decide to go in the direction where with largest size. And then I have exactly this guy then. If I decide to want to go to explore in the other direction, I could. I just have to continue exploring in the place with H. So there are two important things. The first thing is that this is like a sort of miracle thing, because the whole quantum gravity story is built on the idea that, well, if I start from the Poisson point process of quantum disks, if I start with this process, then you can reconstruct this object here. Right? It's non-trivial because the quantum disks are defined up to equivalence classes modulo conformal invariance. They are not naturally embedded. Okay? But the point is that you can reglue the entire space. You have these infinitely many disks. They're all over the place. But there's a procedure, they're coming in at random. There's a procedure to do some patchwork of these disks in order to reconstruct the entire space. Okay? So that's one important message.
So
yes.
You're cutting out those holes, but they're just holes.
Yes.
How come now they become quantum disk with structure on them?
No, because
You put the structure.
I put the structure, this one. So the idea is, I'm exploring simultaneously. Oh, maybe that wasn't clear. I'm exploring simultaneously, and you have the Gauss, you have the CLE, and on the top of the CLE, I put the quantum disk structure of the entire disk. Okay? So a priori, there's no reason that these two things should marry well. But this will work only if gamma squared, you have to have some relation. So gamma squared has to be equal to kappa in that story.
So you get the length from those loops, and you get the...
Yeah. I mean, the length would be the length measured using the Liouville quantum gravity thing on the loop. So another way to say it is, if you don't know what a quantum disk is, you just say, oh, it's easy, right? It's take a Gaussian free field here. Look somewhere in the middle and say, okay, here I have a very small, it's somehow a very small SLE loop. This gives me an infinite measure on loops. You can define the infinite measure on loops, which would be the infinite measure of loops as encountered by this exploration mechanism. And then you say, well, here, this gives me an infinite measure on not only loops, but loops which have a structure, which is a structure, the e to the gamma given there, which is the e to the gamma given by the Gaussian free field in there. So you see, it's not just the Gaussian free field in the loop. It's just, if you imagine the loop is embedded in the entire plane, you take the Gaussian free field in the entire plane, and then you just restrict it to the small loop. That's where this free boundary type structure arises on the boundary. And this infinite measure is just the quantum disk. Right? It's like, take a SLE loop, take a full plane Gaussian free field, restrict it to here, then you have this quantum surface. Okay? Now, if you take this Poisson point process of quantum surface, the point is that here, once you discovered this loop, somehow seen from the outside, there's no correlation anymore. It's just the only thing that you need to look at is the length. So there is a miracle. Now, the second miracle, I just want to not to forget because time is running out. So the second very important feature here is just the formula of what are the positive jumps where this, what is the asymmetry here. I told you to describe all this, you need I. Okay? And this I, of course, doesn't surprise people from planar maps because they see similar things coming up if one believes in all the conjectures. This I is just minus cosine 4 pi over kappa. So it's as beautiful as a formula you can get. So you see that when kappa goes to, when kappa is equal to 4, this thing is 1. Right? So that means that the ratio between the positive jumps and the negative jumps is 1. And for some reason, I don't want to, this is not so surprising. On the other hand, it's all, as soon as kappa is larger than 1 and smaller than, larger than 4, smaller than 4, then this thing, you have more negative jumps than positive jumps. And this ratio goes to 0 when kappa hits 8/3 on the one hand. That's because, then the loops become tiny and most of the space is made out of holes. So it's like just doing the SLE. So, the kappa goes to 0 version of this thing would be earlier result by Scott about SLE6 in okay, no, okay, no, okay, I don't want to. You probably know that SLE 8/3 is nicely related to square root of 8/3 quantum gravity, and you probably have seen papers by Ewain and Jason on So this would be corresponding to the case where somehow here there are no loops left. You just have SLE6, you're doing the exploration of the empty space, and you're cutting out these quantum disks you're just cutting out stuff. You don't create loops. Everything is on the outside. And when kappa goes to 8 here, this goes to 0, and that corresponds to the fact that you're looking at the scaling limit of the uniform spanning tree, piano curve. That's just one loop. There's no empty space. You discover the full loop, full space, and that's it. Game over. You have discovered everything. So there's, again, in that case, somehow okay, you can view the loop from either side, on either side, but that's also going to basically going to 0 limit. Now, there are versions of these results. For kappa larger than 4, and these are actually quite fun and quite challenging. Because then, it tells you what the definition of a quantum disk is you have, these loops have double points now. They are like that. And you want to define this as equivalence classes of, the structure, what you see when you see this in the full plane Gaussian free field story. And here, the idea is to say it's modular conformal invariance, but you have the bottlenecks here. So what you do about, the conformal invariance of the bottlenecks, well, you just say, it's the equivalence classes, you have different connected components, and they're attached by one point, but you're allowed to squeeze that there. Okay, time is off, so I think one thing I'm not always very bad at being elegant is being on time at the end of my lecture, so I should really try to stop now. So thank you very much.